Okay, so what we want to discuss now is something that came up already several times. How many solutions does a system have? And we saw examples where we had a single solution, no solutions, or infinitely many solutions. And in order to do this, exploration of the number of solutions, we're going to need a couple of definitions and then a theorem. So here's the definition. Let A, this is a general definition for a general matrix. It's not only related to systems of equations, okay? Let A be a matrix. The number of non-zero rows in a row echelon form obtained from A using elementary row operations is called the rank of A, denoted either rank A, or in short, just R of A. Okay? So this looks kind of like a mouthful, but let's understand what's written here. You start with a matrix. You can't see its rank. When you have a matrix A, you don't know its rank. It's not something you can know how many rows it has, you know how many columns it has, you don't know its rank. In order to find its rank, you have to start performing elementary row operations, the ones we discussed in the previous lesson, until you reach a row echelon form. The row echelon form is not unique. Okay, there are several of them, but there's a hidden statement here that the number of non-zero rows in a row echelon form is invariant. So it doesn't matter which row echelon form you happen to land on, it's going to have the same number of non-zero rows. Okay, so you do these elementary operations, take as many steps as you need, finite of course, get to a row echelon form. Remember, the row echelon form, all it says is that the number of zeros preceding to the left of the pivot element in each row increases from row to row. Right? That's the definition of a row echelon form. Once you're there, count how many non-zero rows that one has. That's, by definition, the rank of the original matrix A. Clear?
What do you mean by non-zero rows?
Rows that have entries which are not zero. You can have a row that has 0, 0, 0, 0, 0, 0, 0. That's a zero row. Okay? A non-zero row is a row that not all its elements are zero. Okay? So is it clear what the definition means? It's tricky because you can't read it off the matrix itself. You have to first do this algorithm. Okay? Okay. So several remarks. So one, the rank does not depend on the way we do the row reduction. Right? The row reduction you can do, at each step you have different things you can choose to do, right? And each person is going to choose something else to do, and the rank of A doesn't depend on the route you took, the route you chose, okay? And or on the row echelon form you reached. Okay, so there can be many of those, and the rank is still going to be the same. Okay, this, I wrote it as a remark. This is a theorem. Theorems require proof in general, but since this is not a mathematics class, okay, it's just a mathematics course for non-mathematics students, we're not doing all the fine proofs in detail. Okay, and the proofs I'm skipping are usually belong to two categories. The first proofs I tend to skip are the ones that are just kind of redundant, right? So when we had a theorem with 11 different properties of matrix multiplication, checking one or checking the other is kind of the same idea. I did a couple and asked you to do the rest on your own, okay? The other theorems that we skip are the ones that are just too costly in terms of time, okay? Maybe complicated, maybe require very abstract writing, and we skip those as well. Okay? If you're interested, it's very good practice to open a book, find the proof, and get a real feeling for these things, and understand why some seemingly trivial statements are indeed not trivial to prove. Okay? Like the fact that the canonical form is unique. Okay? So that's the first remark. Another way of saying this, by the way, is that if you take two matrices that represent the same, that represent equivalent systems of equations. Any two matrices, any two equivalent systems of equations have different matrices that represent them, but they're going to have the same rank. Okay? Because when you reduce them to row echelon form, if they're equivalent systems, or even if you go all the way to the canonical form, you're going to get to the same canonical one because it's unique. Do you understand what I'm saying? Okay, so maybe let's write that. Matrices that correspond to equivalent systems have the same rank. Okay? Okay. And here's the theorem. I just want to make maybe one more remark. Let's call it remark number 3. In everything we did so far with matrices, we considered only row operations, elementary row operations, and the row echelon form, and the reduced row echelon form, and the rank was defined in terms of the number of rows which are non-zero. Everything was working with rows, okay? And the reason we did that, the reason we're clinging only to row stuff, is because that's what corresponds to systems of equations, okay? But in theory, you can do everything in terms of columns. You can do elementary column operations, okay? You can define the rank via columns, the number of non-zero columns in the column echelon form, and so on, okay? And the only thing you have to be careful is that no longer corresponds to systems of equations. If you change two columns of a matrix, that's doing something very significant to the system, which does not preserve the solutions. Okay? So doing column operations is something that's well defined. You can do everything that we did with columns. It's just no longer related to systems of equations. Okay? So remark number 3, I'm really going to put in parentheses here and write, one can define. It's straightforward how to do it. Just replace row by column throughout. Define column operations, elementary column operations, column echelon form, column echelon form, rank in terms of columns. Dot, dot, dot. Okay. But it's not related to systems, and that's why we don't do it. That's why it's in parentheses here. Okay. But it turns out that the rank by rows, which is what we defined, is the same as the rank by columns. Okay, so the reason I'm saying this is that in practice, once we get used to this, you may have a matrix of 150 rows with only 2 columns. And determining the rank by columns is going to be very easy. Okay, very easy, because there are only 2 of them. And that's going to be the same as the rank by rows. So you don't have to carry calculations with 150 rows because you know the rank by columns, and that's the same as the rank by rows. Okay? But it's not related to systems. That's the important. Okay, maybe I'll emphasize that as well. One can define but not related to systems of equations. In fact, that's not precise either, because if you happen to write your systems of equations vertically, then it is going to be related. I don't know how they write it in China, for example. In China, they sometimes write from top to bottom, right? So maybe they write their system, maybe they write their math that way, and then then it would be related. Okay, but the way we wrote systems as lines from left to right, it corresponds to row operations. Okay, clear? Okay. So all of this was really remarks. Here's the theorem, what we're leading to. So let AX equals B, AX equals B, be a system of M equations with N unknowns, N variables. Then, so it's going to have 3 parts. 1, the system has a unique solution, a single solution, if and only if the rank of A is the coefficient matrix, coincides with the rank of the augmented matrix. Remember what A star is? Right? Let's maybe write it here. Just a reminder, A star is the augmented matrix. It's A and then an extra column with column vector B of the free coefficients. That's A star. Okay? And both of these equal precisely to N, to the number of unknowns. That's the only situation in which you're going to have a unique solution. Okay? 2, if the rank of A and the rank of A star are different, if they're not equal, then there is no solution. And 3, if, this should be a capital if R of A equals R of A star, but it's less than the number of variables, less than n, then the system has infinitely many solutions. And we can say more. We can say how many degrees of freedom we have. How many of those n variables can be chosen randomly, and how many are going to be dependent on them.
N minus a.
Right. With n minus the rank of A degrees of freedom. N minus the rank of the variables are going to be independent, and the rest are not. Okay? So once again, this is a theorem that whose proof takes more effort than we're gonna invest in this course. However, I am going to do an example, and the example is going to kind of reveal why all of this works. Okay, why it is true. Okay, so that's what I want to do next. It's this example, and again, it's going to be kind of long. Okay, it's going to take a bit of details, but it's really going to reveal each of these situations and why in this case there's a unique solution, and why in this case there are infinitely many solutions. Okay, and in particular, this, if you look at this theorem for a second, you can see that these three possibilities exhaust all the various possibilities, okay? Either the rank of A is equal to the rank of A star, or it's not. If it's not, that's it, no solution. If it is, either it's equal to n or it's less than n. It can't be bigger than n because the matrices, the total number of rows can never be smaller than the rank, right? The rank is how many non-zero rows you have. You can't have more non-zero rows than rows, okay? So these exhaust the two possibilities here. So these are the only three possibilities, and in particular, it answers a question that we posed a while ago. Can there be 7 solutions? Okay, and the answer is no. It's either a unique solution, no solution, or infinitely many of them. Okay? Okay, so here's our example. So we're going to consider a system of equations with a parameter. Okay, so the parameter I'm going to call lambda. It's the lowercase l in Greek, lambda. And here's the system. Lambda x plus y plus z equals 1. X plus lambda y plus z equals lambda. And x plus y plus lambda z equals lambda squared. So how many equations do we have? 3. So m is the number of equations, 3 equations. How many unknowns do we have? 3. X, y, and z are the unknowns, and lambda is a parameter. Okay? And what we want to do is kind of explore for which values of lambda do we have a single solution, for which values of lambda do we have no solutions, and infinitely many solutions. So that's what we're going to do. So for which values of lambda are there, let's call it a unique solution, 2 infinitely many solutions, and 3, no solutions. Okay? And we know by this theorem that it's probably going to depend on setting up the corresponding matrix form of this and finding the rank. Okay? So let's do that. So first of all, what's the corresponding matrix form of this system? It's going to be lambda 1, 1. I'm going to right away write the augmented form. Okay? Lambda 1, 1 bar 1. 1 lambda 1 lambda, and 1 1 lambda lambda squared. Note that lambda is just a parameter. It's okay to have lambda squared here. Okay, the variables, it's a linear system. The variables can only appear with coefficients, no x squared or xy or things like that. Okay, so let's write the system. We're going to need a new empty board here. And what are we going to do? How do we tackle this problem? Well, we have to find the rank of A and A star, the rank of the matrix and the augmented matrix. And how do we find rank? We do row operations until we reach the echelon form, right? That's the definition of a rank. Reach the echelon form, count how many non-zero rows you have. Okay, so that's what we're going to do. So here's the augmented matrix representing the system. Lambda 1, 1, vertical bar, and then 1. 1 lambda 1 lambda, 1 1 lambda lambda squared. Do you agree? Everybody? Okay. So now let's start doing these operations. It's again a bit of practice in row operations, trying to get the system to the form that we wanted. Okay, to the echelon form. The first thing I want is to have a 1 up here. Okay? One thing you can do is divide by lambda. That's something you may want to avoid as long as you can. Because in dividing by lambda, that's you're assuming that lambda is non-zero. Otherwise, you can't divide by lambda. And that assumption just breaks into two cases. If lambda is non-zero, divide by lambda and continue. If lambda is 0,
just put 0.
Put 0 and solve it the other way. Okay? So, in general, anytime you're dividing by something, you have to make sure it's non-zero. If you can do other things, do other things. Don't break it into situations if it's not necessary. Here, how can we get a 1 here without dividing by lambda? We can just swap two rows, right? Put this row up here and you have a 1 there. Do you agree? So that's what I'm going to do. I'm going to swap row 1 and row 3. So I get 1, 1, lambda, lambda squared, 1, lambda, 1, lambda, and 1, sorry.
Lambda 1 1 1.
Lambda 1 1 1. Okay? So I have this 1 sitting where I wanted it. Let's kind of put it in a box to know that we're happy about it, and let's continue. So the next thing I'm going to do is I'm going to make these two into zeros, right? That's the next step. And the way to do that is to replace R2 with R2 minus R1. That would make this one a 0. And then replace R3 with R3 minus lambda R1. That's fine. Adding and subtracting multiples of one row to another doesn't require the scalar multiple to be non-zero. If it's 0, fine, you didn't do anything, right? So let's see what we get. We get 1 1 lambda lambda squared. 0 lambda minus 1, 1 minus lambda, and lambda minus lambda squared. And 0, 1 minus lambda, 1 minus lambda squared, and 1 minus lambda cubed. Do you agree? Okay, and let me put squares now here. This is what we did in this step, and these are the elements that we're happy about now. Okay? what I'm going to do now is not a row reduction step. I'm just going to rewrite this. I'm going to rewrite the exact same matrix differently because I want to write everything in terms of this 1 minus lambda thing that is kind of hidden in all these blurry terms. Make your matrix a bit bigger because we're going to need a bit more space. So it's going to be 1, 1, lambda squared, 0, lambda minus 1, minus lambda minus 1, and minus lambda times lambda minus 1, and 0, minus lambda minus 1, minus lambda minus 1, lambda plus 1, and, oh boy, minus lambda minus 1, lambda squared plus lambda plus 1. Okay, I assume you know how to carry out these sort of tricks. It's in fact just finding roots of polynomials. We discussed this at length when we discussed polynomials and finding roots. Okay, so good? Okay, so now I really want to divide everything by lambda minus 1. That would make life a lot nicer, right? Because all these lambda minus 1s would disappear. So I really want to multiply R2 and R3 by 1 over lambda minus 1. And in order to do that, I have to break it into two situations. Either lambda equals to 1, in which case many, many zeros are going to appear here, or lambda is not 1. Okay, so let's write it like this. And let's maybe use red and write, so this is going to be the first case. If lambda is not 1. Okay, and I'm writing it in red and remembering that I have to handle the other situation separately. So if lambda is not 1, I can do R2, replace it with 1 over lambda minus 1 R2, and in the same step, let's do it for R3. R3, 1 over lambda minus 1 R3. And what we get is 1, 1, lambda squared, 0, 1, negative lambda, and 0, negative 1, negative lambda plus 1, and negative lambda squared plus lambda plus 1. Do you agree? Okay, good. So now what we're happy with is this dude here. So this is the pivot element in the second row, right? It has an increasing number of zeros preceding it compared to the previous row. And now what we want to do is make the element underneath it a 0, right? We're carrying out the same idea as we did in previous calculations of the sort. So how do I make this one a 0? We add row 3 and row 2, right? So what we're going to do now is replace R3 with R3 plus R2. And we get, and remember we're still under the assumption that lambda is not 1. Okay, so we have to remember to go back and collect assumptions like that and handle them separately later. Okay. So R3 equals R3 plus R2. What we get now is 1, 1, lambda squared, 0, 1, negative lambda, 0, 0, minus lambda minus 2, and minus lambda squared minus 2 lambda minus 1. Okay, good. And now, remember, we want to make this one into a 1. Okay, let's first put a box around what we achieved in this step. Okay, you can see that we're heading towards the row echelon form, right? Let's make this one into a 1, and then we're happy. So, last step, I want to divide by minus lambda minus 2. So for that, I'm going to have to throw in another assumption that lambda is not equal to 2, right? So where's the red? There it is. That lambda is not equal to negative 2. So if lambda is not equal to negative 2, then negative lambda minus 2 is non-zero, right? And I can divide by it. So R3 becomes 1 over minus lambda minus 2 R3. And what I get is 1 lambda squared, 0, 1, negative lambda, 0, 0, 1, and here I get a big expression, minus lambda squared minus 2 lambda minus 1 divided by minus lambda minus 2. Good? Okay. This is row echelon form. From this I can read the rank of the original matrix. Okay? Do you agree that this is row echelon form? Okay? All the pivot elements are 1, which is not even required, but we said let's do it, it's nicer. And in each row, the number of zeros preceding a leading coefficient increases. So here there are 0 zeros to the left, here there's 1, here there are 2. Okay? So this is row echelon form. Now we know the rank of the original matrices. Okay? So in this case, R of A, let's write, if lambda is not equal to 1 and to negative 2, those were the two assumptions that we made along the route, right? Then, what is the rank of the original matrix? Okay, and I'm only looking at the original matrix, at A, without this column. Its rank is 3. There are 3 non-zero rows in this matrix. What is the rank of A star with this column? It's again 3, right? There are 3 non-zero rows in this augmented matrix, right? So then R of A equals R of A star equals 3, equals the number of variables. Do you agree? So this puts us in the situation of the first part of the theorem. Let's glance at it for a moment. The system has a unique solution if R of A equals R of A star equals the number of variables, 3. Now let's think, why is that true? Let's go back to our example. What happened here? We got to this stage. What are we going to do next? I'm not even going to do that because I wasn't asked to find the solutions in this case. Okay? But I know how I'm going to do it. I'm going to continue doing these row reduction operations until I get to the canonical form. In fact, I already know that I'm going to have zeros here, here, and here, right? Because all the elements in the column of a leading element are going to be made 0, right? So in fact, I'm going to have a very nice A, 1, 0, 0, 0, 1, 0, 0, 0, 1. I don't know what's going to happen here, but do you agree that the solution is going to be evident? There's nothing left to be done, because this is going to stand for 1 times x1 equals this. So that determines x1. Do you agree? Plus 0 x2 plus 0 x3. So it's going to fix x1. This row is going to stand for, maybe let's write that, okay? So there is going to be a unique solution, and we know how to find it. Okay, this is going to correspond to 1 times x1 equals what's ever written here, 1 times x2 equals what's ever going to be written here, and 1 times x3 equals whatever is going to be written in the third coordinate of B. Does everybody see that? Is it clear? Okay, so that's why there's a unique solution. we're not going to have any degrees of freedom in this case. Okay, clear? Okay, so this is not a proof of the theorem, of course. This is just exhibiting the idea by an example. But it's just supposed to convince you that this is precisely the situation where you're going to end up with a system, an equivalent, simple system of equations, where each equation kind of determines a variable, and there are exactly enough of them to fix all the variables. Okay, clear? Now we're not done because we made two assumptions here along the way. So now we have to take, so this is if lambda is not 1 and not negative 2. What if lambda is 1 and or is negative 2? We can't plug them in here. Okay? Plugging 1 or negative 2 in here is a big no-no because we got to this point by assuming that they're not and by dividing by them. Okay? So we have to go back to where we made the assumption and do the substitution there. Okay? So let's do that. So this is the first case. Let's go back to this board. Here is where we made the assumption that lambda is not negative 1. Right? So before we did this step, we have to go here. And here we can plug in, or we can do it in the original, it doesn't matter, but we already made some steps towards the echelon form. We might as well take the last step that we got to before we made the assumption. So let's plug in lambda equals 1 here, right? That would be the case where lambda is 1. So what do we get? We get 1, 1, 1, 1, and everything else is 0. Everything else has a lambda minus 1 factor in it, right? So the second case, I don't want to erase the theorem. Let's erase this. So this is the second case. If lambda equals 1, then we get the augmented system 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, blop. Do you agree? That's the system that we get. This corresponds to the system of equations x plus y plus z equals 1. And that's it. That's the only equation that we have. This says 0x plus 0y plus 0z equals 0. That's not saying too much, and so does this, right? So non-zero rows contribute no information, okay? So we're left with one equation with 3 variables, right? The one equation corresponds to the rank of A, okay? So in this case, R of A equals R of A star. It's the same as the rank of the augmented one, but it's all 1 and it's less than 3. Do you agree? Okay? And there's only one equation, there's only essentially one equation that really carries information in this case. They're all just multiples of that equation, okay? And there are 3 variables. So take any 2 of them, choose them arbitrarily, any value you want. The only one that's going to be fixed is the third one. So you can rewrite this, for example, as z equals 1 minus x minus y, right? And the solution set is going to be take any x you want, take any y you want, and then z has to be 1 minus x minus y. This is the solution set. Okay? So there are 2 degrees of freedom, 3 minus 1, and that's it. Okay, so 3 minus 1, there are 3 minus 1 equals 2 degrees of freedom. Good? And this is going to be the general situation. Once you get to this echelon form, if you have 0 rows, they kind of represent equations that were really fake ones, that carried no information, which may have been hidden as multiples of others and so on. Okay? And you're going to left with only the number of non-zero rows equations which really carry information, which really pose restrictions, okay? Which really pose relations between the constraints, relations between the variables, okay? Is it clear why 3 minus 1 is going to be the number of degrees of freedom, okay, in the example? Good? Okay, so this was the situation where lambda equals to 1. So where lambda equals to 1, we have infinitely many solutions with n minus Ra, n minus the rank of A degrees of freedom. This corresponds to part 3 of this theorem. If the rank of A equals the rank of A star is less than n, then the system has infinitely many solutions with n minus Ra degrees of freedom. Good? Okay, and the last situation we have in this example was the situation where lambda equals minus 2. Okay, and again, we can plug in lambda equals minus 2 at the last step before we decided that it's not and did the next step. Okay, so we need to go here and plug in lambda equals minus 2. So let's do that. And see what we get. If lambda equals minus 2, that's the last case that could happen here. Then let's see what we get. Then what is this going to become? I'm just going to plug in the values. So it's going to be 1, 1. Lambda is minus 2. So I have minus 2, 4. 0, 1, negative 1. 0, 1, negative 1, 2. And 0, 0. And this is going to be a 0 as well now. That's why we made this assumption in order to divide by it. So if we don't, then this is a 0. And then we get something here which happens to be minus 1. Do you agree? Okay. And so what's the situation here? The rank of A, how many non-zero rows do we have in A? A is without this. We have 2 of them. Do you agree? Okay. So the matrix which is the echelon form of A has 2 non-zero rows. Therefore, that's the rank of the original A. Okay? The rank of A is the number of non-zero rows, not in A, in the echelon form of A. Okay? So R of A equals 2, not equal to 3, which is the rank of the augmented matrix, right? The augmented matrix has no 0 rows. Do you agree? R of A star. Okay? And I'm careful to say this, although it's saying many words. These are the ranks of the original matrices. They're determined by reaching the echelon form. Here I can read them. Is that clear? Is that this is a very crucial statement. Okay? It's true that the rank of this matrix is also of the entire matrix is also 3, but that's not what I'm asking about. I'm asking about the original matrix. Clear? Okay. And what's the situation here? This row here, which caused this inequality, right? This row here, which caused the inequality, corresponds to an equation 0x plus 0y plus 0z equals negative 1. Do you see that? Okay? That's an equation without a solution, right? 0x plus 0y plus 0z plus 0z equals negative 1 is an equation without a solution. And that's always going to be the case when the rank of A is less than the rank of A star. There's going to be an equation without a solution, at least one. Okay? No solution. Clear? So this is the idea, this is what why this theorem is correct, and you can really see the various cases in this single example and the way it breaks up according to the values of lambda. Okay? It's not a proof. You can never prove a theorem by taking an example and showing that it works for the example. That's not a general proof. Okay, good? Everybody? Okay, so what we want to do, by the way, so of course you're probably not going to be surprised if I say now that please practice and do several of these on your own, but these in fact are very classical questions in exams. Questions of these sort. I think that probably any exam in an algebra, in a linear algebra course in any university would have a question of this form. Okay, give you a system of equations with a parameter and ask you to kind of figure out in which cases there is a solution, in which cases there are infinitely many of them, maybe find them in one case or another, and so on. This really kind of summarizes the ideas of handling systems of equations via this row reduction method on the augmented matrix. Okay, so please, of course, make sure that you do 1 or 2 or 3 examples, and you know where to find them. Just look at previous exams, and make sure that you understand this process. Okay, there's nothing too deep going on here. It's just a matter of practice. Okay, some things are deep. Okay, this is not deep stuff. This is, I mean, it's a beautiful theory. Okay, it's very, very useful, but there's no deep concepts in the background. It's very straightforward. It's really just spelling out in a very useful way the ideas that these elementary operations don't change the solutions. That's all there is to it, if you think. Okay? And it does get a bit more sophisticated if you try to prove formally these theorems, okay, which we're skipping. Okay, so that's the end of this one.